It's okay.
It's going to be amazing. Yes. It's going to be amazing.
That's probably enough drinks for tonight.
That's so cool. It's going to be amazing. Amazing.
That's probably enough drinks for tonight.
That's so cool.
It's okay. It's okay.
That's so cool.
That's probably enough drinks for tonight.
That's so cool.
It's okay.
My topic is the journey to achieve 1000 TPS for a real-world core banking application. I'm Sidney Chen from PinCap. At the abstract, we all know performance tuning is complicated, especially with distributed database like TiDB. It becomes more challenging when the whole system on ARM64 servers. In this session, we will share how to achieve 1000 TPS for core banking application. And we will show how to apply general methodology to identify the bottleneck, how we explore various tuning techniques, such as improving the CPU memory affinity and slow query optimization. And we believe that these methodology and techniques can be easily acquired by common database users. A little bit about myself. My name is Sidney Chen. I'm a performance engineer at PingCap. Currently, I'm responsible for building the infrastructure for TiDB performance testing. I also involved in many real-world customer cases to help their users to get the maximum performance out of TiDB. The agenda, we are talking about user response time versus database time. And then we'll go through a real-world story. We will show how to do circuit tuning, how to improve the Newman affinity, and talking about one of the key features, prepare plan catch, and the optimized change to stabilize the execution plan. And finally, we will show the how TiDB keep improving for the users to run mission critical OTP. User response time is the total amount of time it takes to process a request. And then usually a user sends a request through the network to application. And the application processes the user request. During the process, it will interact with database multiple times, then get back the response to the user. User response time usually includes the network latency between the user and the application, and the network latency between the application and the database. The blue one is that the time spent inside application, and the green one is that the which we call database time. Is the database processing the request from the application. So it's very important that we get a full picture of user response time. Then we can know where is the bottleneck of the whole application system. Then we can take action to improve the performance. Otherwise, if we don't know where is the bottleneck, we can easily blame each other, each different component, and different organization can blame each other for the poor performance. So it's very important. We know where the time goes for the user response time, where is the bottleneck. Database time is total amount of time database process the application request. And we can drill down database time by different dimension. For example, in this case, database time is consists of the time processing different SQL type, like the select, commit, update statement. And we can also drill down database time by different SQL phrase, like SQL, compile, get token. And there is multiple ways to compute database time in TiDB. For example, we can multiply QPS by the average query latency. We can also multiply average active connections by the delta T. And there's a promises metric to recording the database time. So what we just suggest is to do performance tuning by database time. We can compare the database time to user response time, so we can know if either the bottleneck is inside TiDB or outside TiDB. Okay. Okay, then we go to the real world case. This is a performance tuning project for a core banking application. We will show how to bring the TPS from 1 to over 1,000. The background, together with the application and hardware partners, we need to answer the question, how the application perform on open source distributed database like TiDB and on the new ARM hardware. We have 7 servers, 6 for the database, 1 for the application, and each server has 16 NUMA. Each NUMA has 8 cores and 16 RAM and 1 NVMe disk. The application connects to a database through HA POSI. HA POSI is deployed on one of the database server. We use the TiDB 5.1 version. The workload is actually really heavy. 66% of the statement is select, and 15% of the query is write statement, either commit, insert, and update statement. So when we first run the application, it's very scary. The QPS is just 1. So it's not normal for an OLTP application. We first look at the TiDB dashboard. The QPS inside database is 150, very low QPS, and the 99% percentile latency is over 1 minute. There's a slow query, and there's actually application error complaining that the coprocessor task timeout. And look at the slow query execution plan. It turns out that it is doing 4 table scan on the transaction history table. And it turns out that this is a missing index case. So after create a composite index on the multiple columns, it used the index range scan rather than 4 table scan. The second case, slow query is also doing 4 table scan. There's all predicate for the client relation table, and because index merge is disabled by default, so for every execution, the TiDB need to scan 50 million rows. So we need to enable the index merge feature manually by setting the global variables. After enable the index merge feature, we get the index merge execution plan. So the execution time is reduced to 8 milliseconds. The third execution is related to the index merge. It's actually the same secure statement of the previous statement. We got 2 execution plan even after we enable the index merge feature. One, the back plan is average latency is 1.2 millisecond. So 2 execution plan. The faster one is use the expected index merge execution plan. The bad one is doing 4 table scan. But the strange thing is that for this execution plan, we see there's a demit operator, but we don't have demit expression in our secure test. Why? it turns out that the application set the secure select limit. So this is a no limitation for the index merge feature. When the application set the secure select limit, they can use the index merge feature. So we solve this case by provide a whole face to solve this issue, so that even the application set the secure select limit, they can also use the index merge feature. Okay, after solve these three kinds of slow query, the TPS is up to 30. So we increase the TPS from 1 to 30 by doing slow query optimization. The next one is that we review the cluster config. The current topology is have 3 PD, 3 TiDB, and 6 TiKB. Each TiDB binding with 5 NUMA. And we adjust the topology. We have 1 PD, 36 TiDB, and 6 TiKB. Each TiDB binding with 2 NUMA. Each TiKB binding with 4 NUMA. After the change, the TPS is up to 320. Then where is the bottleneck now? Because we see relative idle both on database server and application servers. For example, each TiDB instance used 100 to 500% CPU, and actually this means that each TiDB is using 1 or 5 cores, but each TiDB is finding 2 NUMA. They have 16 cores, so TiDB has plenty of idle CPU resource. And application server CPU utilization is around 10%. So this is a very common situation that we can get more throughput from the system, but the system seems under very low CPU utilization. We can compare the user response time to database time. The user response time per second is 320 seconds. How do we get this number? We just multiply the TPS by the average transaction latency. And for the database time, the per second is 39 seconds. We can multiply TPS by average query latency. So we divide database time by user response time. The database time just takes 12% of the total user response time. So we know that the TiDB, the database is not the bottleneck. The bottleneck is outside of TiDB. We can identify the bottleneck by compare the database time to user response time, but it actually requires some math, some compute. Is there any easy way? The answer is yes. For TiDB, we have the query duration and connection idle duration metric. So the 80 percentile query duration is 3.8 milliseconds. The connection idle duration, the 80 percentile is 25 milliseconds. This means that TiDB, the connection inside TiDB spend 3.8 milliseconds finish processing a query statement, and it need to wait 25 milliseconds to get another secure statement to process. So this is bottleneck is outside of the TiDB. So just compare the duration versus connection idle duration. We know the bottleneck is outside of TiDB. So we know the application server, both application server and the database server is very low CPU utilization. So where is the bottleneck? We look at the network latency between the application server and TiDB. So we run np state on the server which deploy the HA POSI. We find something very interesting. For the CPU 027, the first NUMA is almost 100% busy. 100% busy. And there's around 40% on to 94% CPU is doing software IRQ. Why? Because for this hardware, all the network software IRQ is routed to the first NUMA to keep the IRQ affinity. And remember, we adjusted the topology that the first NUMA also run the TiDB instance. So this is why the user CPU plus the 6 CPU and the software IRQ CPU is the first NUMA is 100% busy. Then we gather the frame graph on the whole system. There's around 20% of the CPU is spent on the system called finish task switch. So whenever you see very high CPU on the syscalls, it probably means that the system is running very inefficiency. The CPU is spent on the syscalls rather than on the application code. The next step is looking at the impact of the NUMA, because HA POSI and the PD server is running without NUMA binding. So there's high finish task switch for HA POSI. There's a high software IRQ entry and the spin lock for PD servers. So this is the symptom that without the NUMA binding, without the CPU and memory affinity, the system calls will consume lots of CPU resource. So we adjust the topology. We reserve the first NUMA for just for the network software IRQ. We add the NUMA binding for HA POSI and PD server. We double the number of TiDB instance. Each TiDB just bind with only one NUMA. After the change, the connection idle duration reduced from the 25 millisecond to 5 millisecond. And because there is a more workload coming into the TiDB cluster, the TPS is up to 600. Then we see one strange symptom is that the total connection in TiDB is 2000, which match the session limit for the HA POSI. And the total connection is limited to 2000. And after that, the MySQL cannot connect to the TiDB because it reached the HA policy session limit. So we change the HA policy to multiple process mode. Then the total connection is up to 4,400. And we also explore other policy solution in-house. For example, for the Java application, they can use the client-side load balancing. So the traffic between application and the TiDB does not need to go through the HA policy. And we also explore, try the LVS. And it turns out that LVS NLT mode can reduce the connection idle duration time by 42%. So it can be a better option for HA policy. We also fix some environment issues. For example, 3 server they does not have the NVMe disk mounted. So this means the 3 TiKV is running on hard disk rather than NVMe disk. And each server have 2 network cards. One is the 1 gigabit, the other is 10 gigabits, and the 3 TiKV use the long IP to join the cluster, which means they use the slow network card. The solution is to mount the NVMe for the TiKV storage, and we need to scale in to bring down the 3 TiKV, and then scale out to use the high-speed network card. So after the fixes, the TPS is up to 880, but seems the workload is very unstable. There's a response time spikes from the low runner dashboard, and we see TPS drop when the response time spike. So this is a very strange situation. We look at the database dashboard. There's also a small spike in the query latency. If we see 49 percentile duration, there is a huge spike. So this means that the spike in the application response time is caused by TiDB. So we check the system log and the TiKV metric. It turned out that it's caused by TiKV OOM. Why TiKV got OOM? Because when we scale in 3.0 TiKV, we forgot to purge the tombstone, purge the old TiKV instance. So the memory is not released, which caused the 3 new TiKV OOM. So after push the 3 TiKV, and we run 15 scale application server to 15 JVM. Each JVM is binding with 1 NUMA. We get the TPS is up to 1,200. The CPU utilization is around 70%, both on the application server and database server. So this is the best result we get from for this POC. So is there anything we can improve for this performance? Then we look at the database time. We can see that 20% of the database time is spent on the compile secure phase. Compile secure phase is to generate execution plan for secure statement. why TiDB spend so much time to compile the query statement? We then look at the TiDB CPU profile. 18% of TiDB CPU is spent for compile prepare statement, and 36 memory object allocation is also for the compile second phase. Why? If we look at the metric, the plain cache hit OPS is 33,000 per second, and we got 46,000 execution per second. So the plain cache hit ratio is 72%. Without hitting the plain cache, it means that we need to reparse and re-optimize for every single execution. And the percent is not 100%, is because in the version 5.1, TiDB, some kinds of the secure statement can use the plain cache. There is no limitations. So the high compile CPU and memory cost, they have a negative impact on the Golang GC and the query performance. We can pull a trace for one of the TiDB, and we can see for the same secure statement, and the query latency range from 1.5 millisecond to 15 millisecond. So if we explore the stall execution, the go routine need the go routine store and switch to the GC work, which is the green execution. Why the go routine, which execute the secure statement, is need to store and doing GC work? Because there's a high memory and a high object allocation in the database, so you need to do the GC. So in the later version, like in the 5.3, there's a plain cache enhancement. The same workload, running the same workload, it just has 7% of database time is on the compile second phase, and the plain cache hit ratio is almost 100%. So this is a demo that TiDB in the new version, we are improving the plain cache to reduce the CPU and memory cost, and to improve the query stability. The other case I want to share is that the plain stability change. This is the query that has 2 execution plan. One is 62 milliseconds, one is 38 seconds. It's a huge difference. And if you look at the TiDB dashboard, we can see there's a 2 execution plan for the secure statement, which access the MQ producer match table. The predicate is a flow ID and the status, and for both flow ID and status are indexed. So we know that the flow ID maybe we should use the index on the file ID, right? This seems the column seems very distinct. For the long execution plan, we see that the optimized things that the status equal 1, there's 0 rows, the cardinality is 0 for the status equal 1 predicate. So the status index is used. So this calls the long index. Why? This is a case we call always there status. The reason is that MQ producer message table is a message queuing table. During the workload, there's a small number of data with status equal 1, which is the new message to be processed. After the workload, all the message processed and no data with status equal 1. So just before the benchmark, auto analyze is triggered, and there's the no status equal 1 data. The new gather status calls the long estimation and the long index. So this can be confirmed by the updated time on the state histogram view, which indicates the last analyzed time. So we submit a multiple optimizer enhancement. For example, the optimizer need to support locking the status to avoid the unrepresentative status. So to solve this kind of issue, quickly on production system, status also need to store the history status version. So when there is similar issue happen on production system, the DBA can revert to the previous good status version. Okay, the key takeaway of this talk is that on the ARM servers, everything should be binding with NUMA. The JVM, the HA policy, the PD, the TiDB, TiDB, everything should be binding with NUMA. And the core question for performance tuning is where goes the response time, and how to get a full picture and identify the bottleneck. What we propose is tuning by DB time. So you can get the database time from TiDB dashboard, the Grafana performance overview dashboard. We also use various tools like Flame Graph, Performance Top, MP State, Golang Trace, and Profile to help us to do performance analysis. This is the key takeaways. And actually, TiDB is keep improving for mission critical OLTP. For example, in the 5.3 version, we create the plain catch, and for this core banking workload, the plain catch ratio is 100%. In the 5.4 version, we improved the TiDB write performance by introducing async and log engine. In the version 6, we introduced small table catch. So some of the read heavy and small table can be catched at the TiDB side, and we also improve the permissive log to make it in memory. Okay, this is all the topic, and a question is welcome.
Hi, welcome to the virtual Percona Live. This quick session is on why you don't want a varchar32 as your primary key in MySQL. I'm Dave Stokes. I'm a technology evangelist at Percona. I'm the author of MySQL and JSON, a practical programming guide, second edition now available on Amazon. And you might know me from my days at MySQL AB, Sun Microsystems, InfiniDB, and Oracle. Okay, big thing number one, indexes do work, but to get performance, you need to keep them as simple and as small as possible. Well, what is an index? Well, the entire table file must be read from the beginning end without an index. As you can see this person on the right-hand side of your screen. If they want to look something in that tome of paper there, they got to start on the first page and go to the last page to make sure that they found what they're looking for. They found all the references they're looking for. As you imagine, that's kind of time consuming. Now, with an index, you gain the ability to go to the desired information, and it is a lot faster. This unknown picture on the right of an unknown book, if you're looking over the right-hand column and you were looking up bear baiting and Cranmer made archbishop, some guy made a bishop and a bear baiting. If you want to know about that, you can go directly to page 88 without having to read the first 87 pages. Save some time there. So we're talking about MongoDB, which should be your storage engine of choice with MySQL. And MySQL MongoDB uses a clustered index to store the data. And we'll get into that in just a little bit. Now, if you've never seen a B tree, this is it. You can imagine this is the trunk of the tree, and these are the branches, and these are the leaves. Now, this is a very good way to save data for a lot of purposes. For instance, it's very easy to search for a record or a range of records. Now, if we're looking for a record 22, we just take this very convenient path down to this leaf node. And if we're looking for a range of records between 17 and 42, we know roughly the path on where to go to get all the information we want. Very fast searching that way. Now, records in MongoDB are stored by the primary key. Indexes are made up of keys. Now, if you don't pick a primary key, MongoDB will pick one for you, and I can guarantee you that it's not the one you want. So make sure you designate your own primary key. Now, this is roughly what a clustered index looks like. Here's our index, our key, and here's our data. And it's all stored by this key. So all the information that we want to search for is very nicely laid out. Now, primary keys versus secondary keys. There's some confusion on this that I've run into. You want to have a unique primary key that is not nullable for each row. Secondary keys are non-primary keys that are used to access records. So what a secondary key is, it's an index that points to the record to the primary key. And keys are, again, what make up an index. And in all possible, avoid nulls in indexes. They go from a very searchable thing to kind of like a junk drawer that you have to root around in. And do not use GUIDs as primary keys. There's a function that will turn a GUID into a bar binary 32 that works. GUIDs by themselves don't work that way. MongoDB loves primary keys that are monotonically increasing. That means increasing by one or a set number that you have. And you want that to be a set pattern so it knows how to store the data into extents. If you don't have that and GUIDs don't give you that, things get rather messy and slow. By the way, you can use GUIDs as secondaries. So, creating indexes is very easy, but remember they take up space. That means they have to be sitting in memory someplace. They have to be sitting on disk someplace. Also, there's overhead for maintenance. Every time you do an insert, update, or delete, the system has to handle that, which can slow down your queries on a very busy system. So let's run through a real quick demo. We're going to create a schema called test, and we're going to use test. We're going to create a table called X, and we're going to have a column called ID. That's an integer, unsigned, not null, auto increment, and we're designated as the primary key. And then we have C1, which is an integer, and C2, that's an integer. Now, if we show create table, it comes back and tells us that we do have our primary key. So all the records are going to be stored by this ID number. And every time we insert a record, this value is going to be auto incremented. Now this is a little bit bigger view of that for those like me that need that. So ID is int unsigned, not null, auto increment. Once again, every time we insert a record, this number gets bumped by 1 or whatever our preset increment mark is. So int versus big int. I see a lot of things on various websites saying, oh, just automatically make everything a big int instead of an int. Well, int gives you a range of 0 to 2,147,483,647 on 4 bytes of storage. Now, that is a big range. And are you really going to have that many customers? Are you really going to have that many items that you need to track? Well, if you do, you can use a int and use 4 bytes. Now, that is unsigned, where you're not having to worry about negative values. You're just using it all as positive. Now, big int unsigned provides a range of 0 to 2 to the 63 on 8 bytes of storage, roughly twice the storage there, or exactly twice the storage in there. Now, are you realistically going to have more than 2 billion of anything? 2 billion customers, 2 million serial numbers? If not, save space, memory, disk, and bandwidth by going with an int. So we created our table, go in and insert 100 records. And now if we run a query, select star from our table X, where the ID equals 7, explain, which will show you what the query optimizer wants to do with your query to return the data you requested. It says, okay, we're going to go out there and look on table X. We have a possible key that we could use to look at, which is the primary key. The key we actually use is the primary key, and the key length is 4 bytes. And this is the actual query that it would run down here. That's the query plan. Now for comparison, let's create another table. It's another integer, unsigned, not null, called bad ID. And note there's no primary key. Now we also go back and insert records. And when we go out there and take a look at our record, or we're going to say, okay, we're going to select star from table Y, that new table, where the bad ID equals 7. The optimizer comes back and tells us that it's guessing that it's going to need to read 10 rows. And to get that, it's going to have to read the entire table. Well, there are 100 records in this table, and it's guessing it only has to read 10. It's not a great estimate. Now, that those 10 rows, it says its cost is going to be 10.25. Well, we know it has 10 times more rows than that, and the cost is probably off. This is kind of like someone saying, yeah, I can come to your house and remodel your kitchen. I can do it in 3 days for a cost of X amount, and they're wildly off, and it costs you more time and money and heartache. Now, if we go back and run the original one that we had, we're selecting star from table X, where we do have the primary key. Notice it comes back here and says it only has to read 1 row, because this is an index field. And it says, hey, rows fetched before execution. It's able to get the information it wants just from the index itself. Now, this table is small enough where it doesn't have to actually do a dive into the data to get the information. And that is a lot faster. Only has to read 1 row. And the cost, even though this is a bogus cost, is a lot lower. Now, if you look at the explain format equals JSON on table Y, you get a little more breakdown. It knows there's 100 rows out there, and it's just guessing that it has to read 10 rows. And read cost 9.25, evaluation cost 1.0, and prefix cost 10.25. Over on the other side for table X, read cost is 0, evaluation cost is 0.1. So indexes do work. So we just index everything, right? Not exactly. You don't want to do that. Once again, each insert, update, and delete requires overhead to maintain the index. If you have a table, say 150 columns, and you have indexed each column, and you've indexed multiple columns and done functional index and all that, your database is going to be spending more time doing that overhead than it is actually going to be running your data to the database. Also, indexes do take up space. Remember, they got to be in memory, they got to be on disk someplace, and they going to cause you some bandwidth if it's very large. Okay, varchar. This is the subject of this presentation. Values in varchar columns are variable length. Now, varchars are stored as 1 or 2 bytes depending on length of the data plus the data. So rather than just having the normal 4 bits to hold a number, you have this extra number that goes in there and tells you how long that field is. And by the way, you cannot auto increment a varchar, which means you have to run your own sequencing on it, which makes it even more of a pain in the rear. So what can you index? Well, the good news is you can index a whole lot. Now, I do recommend that you use caution. By the way, if you have a table that you that's already out there, but you want to add an index to, use alter table. By the way, there are invisible columns. So if you have a preset table and you don't want to alter your code where it does a lot of select star, you can actually set up an invisible column that unless you explicitly call out that column, the data doesn't get pulled back, and turn that into an index. So just to show off, create table Z. We have an ID that's now varchar 32, and we made it not null. Put in some data, and we run a summary query, select star from Z where ID equals 7, and we actually go out and get the record. And if you're just playing around, not looking at explain, you're probably happy with that. I mean, it seems to work. You only when you start scaling up do you realize you got problems. Now in this example where I run explain format equals tree, it tells us it has to do a table scan. So as that table gets bigger and bigger, that scan takes longer and longer. And whoops. And notice down here, cannot use access references ID equals 7 on index primary due to type or collation conversion on field ID. So you'd have to do your own conversion to this if you want to match up. And cannot use range access on index primary due to type or collation of index field. So there are ways around this, but they're messy and they're hard. This would be a good case where you have that varchar field actually turned into a secondary index. Whoops, looks like I get this repeated. I'm sorry there. Okay, so no varchar primary keys. That's number 2. You can use secondary indexes in varchar. Secondary indexes point to the primary key, which is hopefully an int or, failing that, a big int. So here we're going to create a similar table. Create table W, ID int unsigned. We could have made this auto increment if we wanted. Have a column called name, which is a varchar 255. And we're going to create an index called name underscore index on that name column. Now, if we take a query, here we're looking for all the record from W where the name is equal to Mac. It comes back and tells us that it is using an index lookup, and it's using the name index, the one we created above, to find that record, and it is returning just 1 row. So this was a short and sweet on why you don't want to use varchar 32s for your MySQL primary key. If you have any questions, please contact me. On Twitter, I'm at Stoker. My email is david.stokes@percona.com. Also, this will be posted on various areas, and I will be checking the comments on that. And I want to thank you for watching. Have a great day.
Hi guys, welcome to Percona Community Live Online 2022. Hope you are already enjoying the presentations and sessions. And okay, so my name is Sakthivel. I am working as a MySQL DBA at Percona, and today I am going to present the topic overview of different alter algorithms and its locking scenarios in MySQL. Okay, so this is the complete demo session. So I am going to show everything in the demo. So I hope it will be helpful for someone. Okay, fine. So this is my agenda of the talk. So I am going to cover the three major topics, which is first one is the overview of different locking options and overview of different algorithms with the demo and the role of old alter table. Okay, which is a parameter, MySQL parameter, and we will see how the alter is working with enable of old alter table and disable of old alter table. Okay, fine. So the first one is the overview of different locking options. So we have totally three locking options for DDL. One is the shared, and the next one is the exclusive, and the next one is the none. Okay, so here shared and exclusive both are the InnoDB row level locking. So you may already aware of it. So the shared means it holds a lock to read a row. Okay, so for example, the shared is for the read and exclusive for the writes. We can tell like okay. So for if one transaction is doing the shared lock on a particular row and the other transaction is also trying to access the same row with the shared lock, then that is allowed. Okay, that is possible. But the other transaction is trying to modify, doing some writes, that is not allowed. Okay, so with the exclusive means that is the transaction. The first transaction is already hold the write lock on particular row, and the other transaction is trying to acquire, read, or write lock, then that is not possible. Okay, so I will show in demo so that it would be helpful and to understand better how both are working. Okay, and the next one is the none, which means I would say there is a no lock. Okay, there will be no lock during the operation. So this is my testing environment. I have installed the my Percona server, which is 8.0.28, and I have created the database class, and I have the table SP test1, and I have the my table is with InnoDB engine, and the table size is around 952 MB. Okay, so what I'm going to do, I have the running Sysbench. Sysbench is running, which will do the read and writes on the table. Okay, and how I am going to test the different algorithms and the different blocking means I will start the Sysbench. It will act as an application and it will do the reads and write on the table Hercules.sb test1. Okay, and we are going to test the alter algorithms one by one with all three locking conditions and see what is going to happen. Okay, so we have the three algorithms, which is copy, in place, and instant. We have the three locking options, which is shared, exclusive, and the none. Okay, so what we are going to do is we will first test the algorithm copy with the shared, exclusive, and none. Okay, then we will go with the next algorithm, which is in place. Then there also we will test with all these three, and finally instant. Okay, so this is the way we are going to test in this demo. So let's see a quick overview about this copy algorithm. Okay, so the copy algorithm means I would say there is a traditional method, and how the copy algorithm is working. Okay, so that is the next question. So it will create the temporary table, new temporary table, and it will copy the data from original table to temporary table. Once the copy of the data is completed, the original table will be deleted, and the new temporary table will be renamed as a original table. Okay, so this is quite expensive operation due to the locking issues. Okay, and here lock equal to shared and lock equal to exclusive, both are allowed. Lock equal to exclusive and lock equal to shared, both are allowed. Reads are allowed with lock equal to shared, and reads and writes are not allowed with lock equal to exclusive, and lock equal to none is not supported. Okay, so let's see how this is working in real life. Okay, so here I have two sessions. I have logged in the same server in the two sessions. So here you can see I have installed the MySQL Percona server 8.0.28, and I have the database Hercules, and there I have the table SB test form. Okay, so I have overall 40 lakhs of records in the SB test one table. Okay, I have overall 40 lakhs records. So here also I am going to log in the MySQL. So in this terminal, in the first terminal, we can execute the alter, and in the second terminal, we can monitor. Okay, we will use the second terminal for the monitor. Okay, so here I am going to, let me go to the varlib MySQL data directory first. So I would like to store something in the physical file as well. So I just go into the varlib MySQL and the database directory Hercules. Okay, so there we have currently we have only one table, which is the SB test one, and you can see the IBD file for the SB test one. Okay, so now let's log in the MySQL and show process list. There is nothing running at the moment. I did not start at the sysbench yet. Okay, so we can start the sysbench first. Screen-x sysbench. So here I already have the command. So I am going to do the OLTP read and write test. Okay, read and write test. And I started. Okay, so sysbench is started now. Sysbench is running in the background in the screen. Okay, and if you check the process list here now, you can see the queries. Okay, here you can see the update queries, which is for the SP test one table. Update SP test one table. I have two threads running with the sysbench, so you can see the two queries are running at the moment. Okay, so you can also verify the master status. You can see that is keep moving. Okay, for the last two numbers, 89 to 97, 97 to 85. So which means some writes are happening in the table, SP test one table at the moment. Okay, fine. So here, show create table SP test one. So this is my current table structure. I have 4 columns: ID, K, C, pad, and I have the primary key for the column ID. Okay, so now what I'm going to do, I'm going to test the copy algorithm. Okay, with lock equal to shared and lock equal to exclusive and lock equal to none. Okay, and let's see what is happening. Okay, so now I'm going to add the index. Okay, and let's see how it is. Alter table SP test one, add index idx underscore k for the column name, which is k, and algorithm equal to copy and lock equal to share. Okay, yes, I'm just starting the alter, and let's see the process list here. And if you see the process list here, my alter is running, my alter table SP test one add index, which is running, and the current state is copy to temp table. Okay, because which we see that when we are using the copy, it will copy the data from old table to temp. I mean the original table to temp table. Once the copy is completed, then it will stop the temp, right? So here copy to table temp table, which is currently in progress. And if you see this update statements, this update and this update, you can see which are waiting for the metadata log, waiting for the table metadata log. And also, if you see the physically, if you see the file, here you can see one more IBD file is created, and the current size of this file is 772 MB. Okay, so that is the temporary table, new temporary table. So we see the how the algorithm equal to copy is working, right? It will work, it will create a new temporary table, it will copy the data, then finally After copied all the data, it will swap the table, right? So that is what this is the new temporary table physically. And you can see here the alter is completed, right? The alter is completed. And let's see again here. Now we have only one table because the alter is completed. The whole original table was dropped, deleted, and the new temp table was renamed as the original table. So currently we can see only one IPT. And if you see the process list now, queries are running as usual. There is no locking at the moment. Okay, so here what I would like to say how the copy is working. To create the new table. So here is a proof. It is creating the new temporary table, right? And here lock equal to shared means it is doing the waiting for the metadata log on the write statements. Okay, it will write only on the write statements. So reads are allowed. Okay, so here you can see the update is waiting for the metadata log, and here the next update which is waiting for the metadata log. Okay, so this is what I would like to say with this algorithm equal to copy and log equal to share. And now let's drop this index and we can recreate the index with the same statement, but log equal to exclusive, and let's see. Okay, alter table sp test1 drop index idx underscore k. Dropping the index is not going to rebuild. Okay, it will be quite fast. Okay, so now let's execute the alter again with lock equal to exclusive. Exclusive. Okay, so we previously we run algorithm equal to copy and lock equal to shared. Now we are going to run algorithm equal to copy and lock equal to exclusive. And let's see. Okay, I just started the alter, and here I'm going to monitor the process list. So here, if I see the process list, now select statements also waiting for the metadata log. So here you can see there is this select is waiting for the metadata log, and here is the one more select which is also waiting for the metadata log. Okay, here we are using the algorithm equal to copy. So if you see the physically, then temp table might be created. Yeah, it is created. And you can see the temp table size from 512 MB to 576 MB because the data is copying from original table to temp table, right? So you can see this table is getting increased, size is getting increased. So see, now it is 800 MB. So once it is completed, then it will swap the table. Okay, still you can see the logs are happening, and this query is waiting for more than waiting for 52 seconds, and this is also 52 seconds, and waiting for the metadata log. Selects are waiting for the, the reads are waiting with the exclusive log. Okay, now the alter is completed, and if I see the show process list, now everything, the log was released and everything is good. So I would like to explain how the copy is working. Okay, you can see the temporary file under the data directory, right? And you can understand the difference between the shared and exclusive. Shared means selects are allowed, only the writes are blocked. Okay, exclusive means selects and writes both are blocked. Okay, so that is the difference between shared and exclusive. Okay, fine. So now this alter is completed. Now let's drop the index and recreate the index with lock equal to none and algorithm equal to copy. Let's try this, and you can see the query got the error like lock equal to none is not supported. Recent copy algorithm record a lock. Try lock equal to shared or exclusive. Okay, lock equal to none is not supported when you are using the algorithm equal to copy. Okay, fine. So this is about the copy algorithm, and the next one is the in place. So in place is introducing the MySQL 5.6, and it will not copy the data like the previous method. It will do the table rebuild in place. Okay. So here so in copy, it will create the new table and copy the data, then sort the table, right? But here how it is happening means it will create a temporary file, and it will log all the modifications, insert, updated it, all the modifications in the temporary file, when during the completion phase, alter completion phase, it will apply all the modifications in the table, then do the then the alter will be completed. Okay, so it will create the temporary file, it will capture all the modifications, and during the alter execution completion, it will apply the changes and alter will be completed. So this is how the in place method is working. So you can control the size of the temporary file using this variable InnoDB online log alter log max size. Okay, so you need to make sure you have the big size of this variable. Okay, when you are doing the big table, busy table, if you are doing some busy table which the tables are getting frequently modified, then you need to make sure you have the good amount of size, some big number, 5 GB or 10 GB for this log file size. Okay, so that your alter will not get failed. Okay, if the temporary file is filled, then your alter will be failed. So you need to make sure you have the good amount of the size, good size for this table, for this variable to allocate. And here the advantage is lock equal to none is supported, but in copy algorithm, lock equal to none is not supported, but in place lock equal to none is supported. Okay, that is the one of the biggest advantage using the algorithm equal to in place. So now let's see the demo with the in place. Okay, so here I'm going to execute the same alter table add index query, which first shared and algorithm equal to in place. And the algorithm equal to in place, and I am using lock equal to shared. Okay, I executed the query, and let's monitor the process list here. And if you see here, again, I am having the waiting for the metadata log, table metadata log for the write queries, for the updates, for this update also, I'm having the waiting for the metadata log. And if you see here, this altering, you can see the altering table, but for the copy to temp table, you will see the state which is copy to temp table. But when you are running with the in place, it is altering table, because here we are not copying the data. All the activities is happening in the same table itself, right? It is just rebuilding the table. So here you are seeing the altering table, but when you are using the copy, you will see the copy to temp table. Okay, so but when we using the shared, the locking is same. Here also selects are allowed, updates are getting locked with the waiting for the metadata lock. And here you can see the alter is completed, and it took around 17.96 seconds. But if you see this copy algorithm equal to copy, it might take some nearby 1 minute, 56. Why? Because it need to copy the data from one table to other table, and it need to sort the table. But here it don't need to copy the data, right? All the processes are happening in the same table. So this method is quite fast compared than the copy. Okay, so now I'm just dropping the index, and I'm executing the same alter with lock equal to exclusive and algorithm equal to in place. And let's see what is happening. Okay, just started the alter, and I'm seeing the process list. Here you can see waiting for the metadata log for the select queries. This is the same behavior we see in the copy as well, right? Waiting for the metadata log for the selects as well. Okay. And here also the table is in the altering table state. And here also the alter is completed quite quick, within 18 seconds, because as I told earlier, here we don't need to copy the data from one table to other table. All the processes are happening in the same table. So this method is quite fast compared than the algorithm equal to copy. Okay. So after the alter is completed, the logs are released, and they are running without any issues. Okay. So this locking, when compared to locking, shared and exclusive, both are happening same like copy, right? When we have the shared lock, selects are allowed, but writes are not allowed. Update deletes are blocked, waiting for the metadata lock. When you have the exclusive lock, selects and writes, reads and writes, both are blocked using the table metadata lock. Okay, this is same for copy and what is this? In place, both. Okay, same for copy and in place. But here but if you come to algorithm equal to copy, lock equal to none is not supported, but algorithm equal to in place is supported for the lock equal to none. Okay, you can run the alters without any lock by using the algorithm equal to in place. So let's see that. Now algorithm equal to in place and lock equal to none. I'm doing the same index creation for it. And if I see the process list here, you can see okay. Let me fix this. Actually, there is a commit running a long time. It might be disk issue. Yeah, my disk is filled 100%. So I need to fix this first. Let me fix this. Oops. So what is okay? So actually, I have around 15 GB of this, and I'm just removing this pin lock. This is not recommended, but still I don't have any other choice. So I need to update the index file as well. Okay, I just removed the bin lock, which is starting from 19, right? Bin lock 19. So I need to remove that entry from the bin lock index file as well. Otherwise, it will create problem. Okay, so when you are removing the bin lock manually, so you need to make sure you need to update the bin lock file as well. Okay, so I did. And df-th. Okay, now I have 2094. And let me clear the other bin logs. Show binary logs. I think it needs. Okay, cool. So I'm just going to purge the binary logs. Purge binary logs to. So binary logs df-th. Oops. Okay, so now I have 43% utilization. Use surplus, and let's verify that all good. There was some commit was hang, right? Show process list. Yep, all good. Fine. So this is unexpected. My disk was full, so I just removed the binary logs and I just freed some disk space. Now all good. Now we can experiment. Now back to topic. We can experiment the algorithm equal to in place and lock equal to none. Okay. Yeah, it is started. And show process list. So here you can see my update is happening without any issues. There is no metadata logs, and my alter is also happening. And here also one more update which is updating. It is happening. So I don't see any locking issues when using the algorithm equal to in place and lock equal to none. Okay, so this is also completed, and I don't see any issues. Okay, so this is the this is how lock equal to none is okay. Okay, so so we see two algorithms which is copy and in place. So we lock equal to shared and exclusive both are supported in the copy and the in place both algorithms. Lock equal to none is not supported for the copy. Lock equal to none is different. So now let's move to the next one, which is instant. Okay, so which instant means this is introduced in the MySQL 8.0.12, and this is only going to modify the data dictionary. Okay, it is not going to rebuild your table or not modifying data. So this we can call it as a just metadata change. Okay, so but it don't have the support for all the alters, It have the limited supports for adding the columns, dropping the columns, modifications, column change, default change modifications, etc. So you can get, you may need to know, right? So what are the operations it is supported and what are the operations it is not supported. Then I would recommend to go to this page. Here you can see all the, for instant and in place rebuild, whatever it is supported, you can see. For example, creator or creating or adding a secondary index, instant is not supported, which is no. In place is supported, which is yes. So similarly, for all the operations, you can get the details here in this page. Okay, so if you before executing the details, you can get the information, which algorithm you can use. Those informations you can get it from this page. This is very useful page. Okay, to know that. So fine, and now let's do that. Let's test the instant by adding the column. Okay, because adding the indexes is not supported with the instant algorithm, so we can try adding the column using the instant and see how it is happening. Okay, so here, so this is running, the system is running. You can see the update, and here alter table sp test1 add column te underscore id in not null default one algorithm equal to instant, and let's try the log. Okay, log equal to shared, and we can see, incorrect usage of algorithm equal to instant and log equal to none, shared, and exclusive. Okay, similarly, you will get the same error for all those. Exclusive, same thing, same error, and when I am using the none, I will get the same error. Okay, so then how to execute the instant alter means you don't need to provide any locking options, just algorithm equal to instant is enough. Okay, so I just executed and the query is completed within a second. Okay, just took 0.73 seconds to add a column. Okay, so this is very, very fast. So as we see before, how the instant algorithm is working means it is just going to update the data dictionary, and it is not going to rebuild your table or modifying data. Okay, just it is going to update the data dictionary. So it will be quite fast, instant. But as I told earlier, it don't have the support for all the alters. It have the limited support. You need to check that document I show you, right, to know what are the operations are supported, what are not supported. And here one more thing I would like to mention from MySQL 8 server 29, which is the very recent release. It has the support to drop the column as well. Okay, you can use you can drop the column using the instant method, algorithm equal to instant. Okay, so this is about all the algorithms, alter algorithms with their locking methods. So let me quickly explain this. So we have three algorithms. One is copy, in place, and instant. Okay. So copy is supported with shared and exclusive. None is not supported. In place is supported with the shared, exclusive, and none. Okay. Instant is not supported with any of the locks. Okay. Just you need to provide the algorithm equal to instant. That is fine. So when you have the lock equal to shared, what happens? It will allow the reads, but it will not allow the writes. When you have the exclusive lock, it will not allow the reads and writes. It will block everything. Okay, you cannot access the table. And when you have the lock equal to none, it will allow the reads and writes, but maybe you can expect some locks during the table alter completion. Okay, when it will try to update all the modification from the temporary file, that time you may expect some locking. But lock equal to none, from my experience, lock equal to none is very good one to go with. Okay, but still, when you are doing the alter, it's in place and lock equal to none, you may get you have the asynchronous replication. There you may get some replication lag that you need to consider. Okay, so this is just a difference between the three algorithms. In place is supported with the lock equal to shared, exclusive, and the net. Okay. And instant is not supported with any locks, but it is very fast. You just need to use the algorithm equal to instant. That's it. Okay, fine. So now let's move to the next one, which is the parameter, MySQL parameter, old underscore alter underscore table. Okay, so let me explain this theoretically how it is working. So when this variable is enabled, the server does not use the optimized method of processing an alter table operation. Okay, so when this old alter table parameter is on, it will not use the optimized method. Okay, it will always go to the traditional method. Traditional method means algorithm equal to copy. Okay, when this variable is off, the server will use the optimized method. Okay, based on your alter statement, it will use the optimized method. So let's see the demo for this as well. So show global variables like old alter table. So by default, this is off. We cannot change this in global. So it will not work. Oh, sorry. It is working. Let me see. Let me confirm this. Okay, so this is actually working. You can do this change. You don't need the MySQL restart. You can change this on global. Okay, but make sure you are reconnecting the session. Okay, after changing this variable. So I already reconnected. Now what I'm going to do, I'm going to execute the alter without mentioning. Yeah, I'm going to add the index without mentioning any algorithm and without mentioning any log. Okay, just I'm going to execute this alter table sp test phone, add index idx underscore k, and column name is k. I'm just going to execute this alter statement, and let's see. You can see waiting for the metadata log. Okay, for the update statements. Updates are getting logged, which means writes are getting blocked. And you can see copy to temp table. Copy to temp table means this is using the algorithm equal to copy. Okay, so this is using the algorithm equal to copy. And so I did not provided any algorithm or locking, nothing. I did not provided nothing. But when I execute just the alter, it is going to the copy to the temp table, and that is the algorithm equal to copy. It is going to the traditional method. Okay, that is what I am coming to say. When this variable is on, old alter table is on. Okay, and I did not provide any algorithm, and I did not provide any locking. It is going to the traditional method, which is algorithm equal to copy. Okay, so now let me off this variable. I'm just disabling the old alter table, and I am reconnecting, and I am going to execute the same alter with the just changing the index name because the index is already existed. So I'm just changing the index name. I'm just executing the alter without providing any algorithm and none. And now see the process list. Now if you see, my delete is executing, and here also altering table. This is not the copy to temp table, right? So this is just altering table, and my delete updates, other queries are executing. You can see the updating. Okay, there is no logs. Okay, so when this variable is disabled, okay, old data table is disabled, the server will choose the optimized method. Okay, so here it choose the log equal to none and algorithm equal to in place method. Okay, so that is what I'm coming to say. I mean, I wanted to show the difference between old data table enable and disable. So if you disable that variable, what it will do, the server will choose the optimized way to execute the alter, And if you enable that variable, it will always go to the traditional method, which is copy method, algorithm equal to copy method. Okay, so this is the role of the old alter table parameter. By default, that is disabled only. So we are good. So whenever you are executing the alter without algorithm and lock, then it will just choose the optimized way and run it. But if you enable that variable manually, then you need to make sure you are providing the proper algorithm and the logging things. Okay, so this is what I would like to share in this presentation. So hopefully this is useful. Maybe you have some questions or comments or concerns, whatever, please let me know. Okay, thank you so much. Bye.
So alerting, it's here in PMM. It's this little bell that sounds like an alert. But before we do anything here, we need to go to configuration. We need to go to settings, and then within settings, we're going to look at advanced settings here, the second option on the left. And here you will see the option to enable integrated alerting. I already have it enabled, so I don't have to save anything, but by default, this is going to be off, and then you're going to have to do apply changes over here. Once you do that, this little tab is going to show up. Like the first time you load this without integrated alerting, you're not going to have the communication tab. After you integrate it, after you enable, and you do apply changes, you might need to come here again to settings and go to communication tab. This is where you will set up the backend communications. So this is gonna allow us to push out alerts. So for email, very simple, we set up an SMTP server. We said who is pushing the alert, like what is going to be the sender, what authentication type. In my case, I'm using login, my username, well, password, if it requires encryption, and then it will allow me to do, and do a quick test. Oops. Okay, I need to enable the email. I already have it elsewhere. I know it's working. I tested it before.
Okay.
Just in case, I might come back here to fix it in the worst case. But this is the simplest mechanism. And of course, if you look closely, it's not asking me for recipients at this time. This was just for testing. So this is just like our SMTP server, right? It's our mail office. So this is not like a fixed recipient thing. So that's one of the nice parts. And then you can set up a Slack. I was trying to set up a communication channel with a Slack, but didn't get the approval from IT on time. But basically, you go through a very simple process where in your workspace, you can create a so-called app, and the app can have a webhook, and the webhook is going to give you a URL, and that URL is what you will actually use here.
And you could do other webhook things as well. So if there's other monitoring systems that allow webhooks, or you want to integrate, you can do that as well.
Mm-hmm. Yeah. I think anything that supports webhook, which is a simple post, thing with a fixed structure. Yeah, you could do that as well. Exactly. So I have my email set up. The next thing is going to integrate alerting. And here comes no alerts. My system is working flawlessly, gladly. So it's a bit weird, but I will tell you, start from the right. Start right to left here. The first thing you want to do is actually set up notification channels. We first set up the communication channel, which is how we are going to send notifications. Now we're going to set up notification channels, which is to whom we are going to push those. So if I would like to add one, I will be able to choose, could be PagerDuty, other webhook, or Slack like we configured before. Again, I'm just going to use email. And I'm going to say P1 alerts, email, P1 alerts, all support. And I will add. I'm not going to do it, but you could add. I don't know, the support team at percona.com. I'm just going to add Matt. Is like that, Matt?
You're going to add me? Oh, he's gonna spam me, everyone.
At percona.com. There you go. And
I don't know why he didn't add himself, but now
okay,
I
can do that.
No. I'm gonna get spammed. I'll take one for the stream.
Yeah, please. And you're gonna join support as well.
Yes.
So now that I have a channel, I will be able to use that channel to deliver alerts. I could also, create another one that is email P2 alerts on duty. Oops. And that will be only Marcos because.
Well, thank you for sparing me those.
Yeah. So you're not on duty. I'm sparing you from the duties. So now I have multiple alert channels. I could go ahead and say, let's create a template. So rules are based on so-called templates that allow us to not have to redefine the whole rule again. So it's an abstraction that will allow us to create many rules later. That is basically the gist of it. There are many already built in for ProxySQL, Postgres, for the node itself, for MySQL, MongoDB, and usually you can just go ahead and come here to alert rules, and you could start adding an alert with one of those. Let's quickly add one of those. So I'm gonna use MySQL MySQL connections in use. MySQL connections in use. Warn. So I'm gonna warn when there are more than, I don't know, let's say 30. And if it has to be, this is the threshold for the alert. And so I'm gonna say when there are more than 30 connections in use. And for how long?
But wait,
Yeah.
so the threshold, like if you look at it, it says it's a percentage. Is it a percentage?
I will show you that in a minute. That's a bit of a mistake, let's gonna say. I think we should report some documentation bugs because when I create the alert, you're going to see where these are coming from. and you will be able to actually understand why it says %. It's a Percona limitation, and I will explain where it comes from. Okay, so just 1 minute.
Okay, I'll hold on. I'm holding on,
Please.
everyone. I'm holding on to myself while I wait
Okay.
for Marcos.
So here it says duration in seconds. So what I'm asking is that this threshold must be exceeded for 300 consecutive seconds. Let's just make it 10 for the purpose of demonstrations. And I'm going to say it's a warning. And here I could create filters for my nodes. So basically in my nodes, I could add, for example, the service name. I'm just going to go with an easy one. But you could make it by cluster. You could make it by node. You could make it by service type, by environment. So there are.
And so, but so for the filters are not SQL filters. Just so people who are used to SQL, these are not SQL filters. This is what was that?
This is MetricSQL.
Yeah,
This is based on MetricSQL, which is Victoria Metrics query language, very similar to PromQL. Like if you're familiar with PromQL, you're not going to have any issues getting there. And there is one other thing I'm going to show you, and that is, I think, one of the main things that people get wrong, and it's so easy to get wrong that I got it wrong the first time. So even I got it wrong. So yeah, filters are just allowing us to say this alert is good only for these nodes or this environment or this type of database. Super useful, right? Because I don't want to check if I have mixed MongoDB and MySQL. I don't want to check max connections the same way in. I'm not able to check max connections in MongoDB the same way I check max connections in MySQL. So I will set service type MySQL. So in this case, I'm just going to say I want it for my MarcosDB MySQL database instance. And here we can see the formula. Again, this is PromQL or MetricSQL. And you can see it's comparing with something called threshold. And this is basically what is going to be emailed to us when the alert goes off.
So that's interesting. So looking at the expression, it's taking the last 5 minutes, so the maximum over the last 5 minutes, and then it's dividing by ignoring job.
So this is a single expression, right?
Oh, okay. Yeah. Okay.
So ignoring job, give me the max connections.
So it is looking for max connections it's looking for the total or the maximum number of connections that were active divided by
the percentage.
So it's making the percentage, which you set it to 30 connections, not 30%. You said
30%.
So.
Yeah. So yeah, I got that wrong because I was thinking in my alert. I'm bad. My bad.
So
it's good that I actually took a look at the template expression because